Hello and welcome to Android Performance Workshop. We find the concept of a 3-hour session unimaginable, so we will be breaking it into 2 sessions. We're going to start out with a talk on memory, and then we're going to follow it up after the break with a talk on other performance issues. I'm Chet Haase.
And Romain Guy.
And I work on the framework team. I work on UI toolkit, UI widgets, graphics, animations, performance, stuff like that.
And I used to work on Android.
And we also work with someone named Diane Hackborn. If anybody knows her online from the Android forums and Stack Overflow, very smart person. She gave a talk internally on memory in Android, how it actually works on the system and how to use that knowledge to optimize the memory that you use in your application. Just things to be aware of in general for performant applications, because these are constrained devices. You actually need to think about memory a little bit more than you do on, say, servers and desktops. So it was such a great talk, I asked her if she wanted to do it externally, and she gave me this awkward look and walked away. She has no interest in doing that, so we thought we would steal her talk instead and recast it for DevOps. So let's go. So why are we talking about memory? Didn't we solve that problem a long time ago? It turns out that Android and mobile in particular are quite different. These devices are really small and they're very constrained, and lots of little decisions that you make, like some of the ones that we'll see in the ensuing slides, can really cause large problems for you that are a lot harder to fix afterwards when your architecture and your APIs and your libraries are sort of fully existing and working but not working well enough. It's a lot better to actually think about these issues up front. And another big issue, of course, is that we always want more. Users want more animations, they want more graphics, you have larger images, you have larger displays, and so there's these constant requirements of increasing demands on the devices, and yet the devices are still really small, the batteries are really small. The amount of power that we can actually run through the system at any given time is very constrained. So how do we deal with these conflicting things where you just have too many requirements placed on the system for it to behave normally?
And what Chet just said, it's not just theory. Those are all problems that we actually run into on the Android team and the Android team as a whole at Google. That means all the Android applications at Google. We're going to talk about it in more details, but recently there was a huge effort to improve memory usage on Android, and we discovered that it was really, really hard to fix those issues after the fact.
So one of the theories, one of the things that people say is, you know what, the hardware is going to get faster. It always does, right? And to some extent that's true. But the reality is, yes, the hardware gets fast, but it also gets cheaper. And so people will still want slower hardware because it provides them a cheaper device. There are emerging countries out there, or there are just people that don't want to spend $1,000 on a smartphone, that want a cheaper phone that does all the same stuff. So yeah, the hardware may be faster this year than it was last year, but that doesn't mean that last year's hardware or the hardware that was current 5 years ago is not still being sold in new devices. And so you still have to keep track of reasonable performance on low-end devices. I think developers tend to run on higher-end devices, and you get a skewed perception of what real people have. Real people have the cheapest device that they can get. So yeah, hardware is faster, but that doesn't necessarily solve your problem, at least not in the short term. So there's a few dynamics in the mobile space. We all want a wonderful experience, right? You have these capabilities that, 10 years ago we were teaching people how to do this kind of stuff on desktops, how to do these animations and translucency when you wanted it to get these nice sort of fading effects there. And everybody got used to that on the desktop, and now they're on smartphones and they want that everywhere. They want these beautiful, smooth animations and wonderful performance and lovely graphics everywhere and high density screens. At the same time, the hardware is slower. These are not desktop PCs, these are not servers. These are constrained devices with constrained battery requirements. And the screens are getting bigger. This is probably our favorite one to fight, is that the resolution of the displays is increasing every year. And it means if you have twice the size of the screen, so it's going to be twice as wide and twice as high, or at least that many more pixels, it's actually 4 times the number of pixels that we have to deal with. And the GPUs and the CPUs are not actually improving at the same rate. So we're dealing with more and more pixels all the time in these higher resolution displays. We have to do more stuff to put it on the screen, but we don't necessarily get increased performance in order to do the computations to do that.
And here's a great example of what higher resolution displays will do to your application. So the first Android device, the T-Mobile G1, would give you 16 megabytes of Dalvik heap. So you had 16 megabytes for your entire application. Today, with 16 megabytes, you can display one full resolution image on a Nexus 10. So in 5 years, the amount of data that we need to process has grown a lot faster than the actual amount of RAM that we have in the devices. And this is why everything we're going to talk about is very important.
Oh, by the way, all this stuff is running on a battery. You're not plugged into the wall. You don't have external power supplies. You just have this little tiny battery that will run out very soon if you're pegging the CPU and the GPU all the time. So you do what you can to conserve battery at the same time. Oh, and by the way, people like to have their phones just magically running for hours and days. So how do you solve all this stuff? By being smarter about memory in general. One of the dynamics that we've noticed in the marketplace is, of course, we developing on the Android framework are always on the latest release. We're developing on the next one out there, and we're thinking about the last couple of releases. So my mindset is pretty much about Jelly Bean, because that's sort of the current raft of releases that we've put out there. They're being used widely in the world. In the meantime, there are still new devices coming out with much older releases that we may have forgotten a long time ago. But again, people like low-end devices because they're a lot cheaper. And one of the reasons in particular that people are still getting phones with Gingerbread on it was because there were lower memory requirements for that platform. Every time we add stuff to the platform, obviously there are increased memory requirements simply because there's more going on there. But these devices don't necessarily have the amount of memory to handle that. Now, we're doing some stuff on the Android team, which we'll talk about later, and we'll talk about in our What's New talk tomorrow as well. But at the same time, you need to be aware that there are devices out there that are very current that users would really like to continue working for a while that simply don't have the capabilities that you're used to on your 1 gig or 2 gig of RAM smartphone that you may have in your pocket. So we're going to talk about generally 3 different areas, but a lot of subtopics in there. We're going to talk about how RAM and memory in general is dealt with on Android, sort of the overview of how things work, and some general tips and guidelines and things to be aware of in the language and the platform in order to create applications that are more optimally using their memory. And we'll talk about some of the tools that we have for actually using memory consumption and tuning your applications.
All right, let's start with RAM. The first thing I want to talk about is 2 different concepts, and we'll get back to those a little later in the talk, but you should keep those in mind. So there are 2 types of RAM that we deal with on Android. We have the clean RAM and the dirty RAM. The easiest way to remember what they are is clean RAM is good, dirty RAM is bad. So clean RAM is a type of RAM that we can page out. So Android does not have a swap. So on the desktop, when you're running out of RAM, the system, the OS, will swap your memory to disk, and usually that's when your desktop starts getting slower. On Android, we do not do that. So all we can work with is the RAM that we have, the physical RAM that we have. However, we do a lot of M-mapping of files. So instead of loading your code in memory as a copy, we just M-map the different pages from the file system directly. And those are clean pages. So when we need more RAM, we can just page those things out to disk, knowing that the data is still there unchanged when we need it later. Dirty RAM is everything that you allocate. So every time you type the keyword new in C++ or Java, or you do a malloc, that's dirty RAM. This is RAM that exists only in memory, and if we get rid of it, we have no other way of getting it back unless we execute your code again. So dirty RAM is very expensive because the only way to get rid of the dirty RAM is to kill the process or to have the application react to some system event saying that we need to reclaim that memory. And you're going to see why dirty RAM can be bad. How many of you are familiar with the concept of Zygote on Android? Do you know what it is? Just raise your hand. Okay.
3.
Yeah,
I think I saw 3.
I think it was 2.5. So Zygote is a very, very important process on Android, and it's one of the biggest optimizations we have to deal with the amount of data that we need to provide to each application. So when you boot your device for the first time, we create that process called the Zygote, and we preload the most common APIs of the framework in that Zygote process. So we preload all the class files, And we initialize some of those class files. So we pre-run some of our code. We are going to load some of our native libraries. And we will even load some of our bitmaps. So all that data that lives in Zygote can be shared between all the applications. So when you start an application, we don't create a fresh process for your application. Instead, we fork the Zygote process. That means that your app starts by sharing all the data from Zygote. So when your app starts, we don't have to reload all those classes. We don't have to reload all those bitmaps. All that data is already available. And Zygote is pretty big these days. I think we have about 8 megabytes of Dalvik allocations in Zygote, and we have a few megabytes of bitmaps. So all that data doesn't need to be created in other processes. So this is a small diagram that shows you what happens exactly. So in Zygote, we preload the framework classes, a bunch of assets, and some native libraries. It can vary from device to device. For instance, on some devices, we can preload the OpenGL drivers. On other devices, we can't. And when you start your app, you have your own memory. So everything in blue on the diagram, that's your dirty memory. So everything that you allocate in your app will most likely be dirty memory that we cannot reclaim without killing your process. Everything that is yellow is basically free. So we try to share as much as possible between processes. So this is a recap of the types of memory we have. So private memory, that's the memory in your application. If it's dirty private memory, that's a bad thing for the system. And this is the most common type of memory on Android. Clean private, we're going to try to mmap files. We're going to get back to this later, but when all your assets, for instance, all the code in your APK, we try to mmap it directly so we can have clean pages, so we can reclaim this memory as needed. And all the shared memory, whether it's dirty or clean, is actually very good because we don't have to replicate that memory across multiple processes. So overcommitting, we just wanted to mention that. It's not very important if you do not write native code. So if you write native code on Android, you will see that we do something called overcommitting. So when you call malloc, for instance, on new, we don't actually commit that memory right away. We just reserve the address space. So you could do a malloc of 1 gigabyte of memory, and it will work. Like that won't fail, even if you do not have a gigabyte of available memory. It's only when you're going to start using the pages of that memory that things might start failing. So the big problem with overcommitting is what happens when we don't have the RAM for that memory that we've already reserved. And like I mentioned, Android does not do swapping. So instead, we use processes as a swap mechanism. We have two types of processes. We have the running processes and the cache processes. So typically, the frontmost application, the application that you are using right now that's showing a UI in front of you, that's your running app. And then all the services running in the background are also running applications. So for instance, if in your app you create a process that you never stop, your app will keep running and that will take up a lot of RAM. When the system decides that the process is not running, it goes into an LRU list. It's a list of all the processes that we've seen. And if you start that app again, we can just resurrect it from that list and just reuse the memory that's already there. If we need more memory in one of the running processes, we'll just go in the LRU cache and we'll just kill processes as long as we need to until we have enough RAM for the running processes.
There's some other dynamics about how we choose which ones should be killed according to the type of process.
It's pretty complicated. You can find information about that in the Android documentation. There are tools that you can execute on your phone that will give you all the information you need to understand when your process is going to be killed or not. But we won't go into those details right now. The point is that having this concept of cache processing is key to the Android experience. Without that, the system will be a lot slower. That's how we can bring back applications really quickly, and that's how we can pretend that we're running so many apps at the same time. New to Android 4.4. So I just mentioned that Android doesn't do swapping, and that's actually not true anymore. So in Android 4.4, if you have a low memory device, so a device with only 512 megabytes of RAM, we're going to swap to RAM. So we're going to swap from the RAM to RAM, but we have a fixed set of memory in physical RAM that's compressed. It's a little bit costly to read and write that compressed RAM, which is why we don't compress the entirety of the physical RAM. But if we're really low on memory and we will have to kill a bunch of processes or running services to be able to start a new application, instead we're going to use compressed RAM. So you don't have to worry too much about that. It's just to give you an idea of what we do behind the scene to make sure that everything works right.
So we use shared memory. I don't know. I don't have anything to say on this screen. Can I go to the next slide?
Sure.
Okay, I'm going to move to the next slide now, where we're going to talk about the different kinds of shared memory. That was just like an introduction. It was kind of a teaser, whet your appetite. So we have different kinds of shared memory. We mmap, as Romain was saying earlier. We can page in your code or resources, and then we can page that back out if we need the memory. We also have Zygote that Romain also talked about. We also have AshMem, which is Android shared memory. These are for particular types of allocations like database cursors and some of the graphics resources.
So we also introduced in Android 4.4 a new feature of the Linux kernel called KSM, or kernel same page merging. So the idea is that you have all those pages of memory and RAM, and a lot of those pages will contain the exact same data. So we should be able to just merge all those pages into a single one and save a lot of physical RAM. So a great example of that is bitmaps. So a lot of bitmaps on Android have a lot of transparent pixels. So if you imagine a large bitmap that has, an entire row of transparent pixels, that's all zeros. Now imagine that in a lot of applications running on the system, you have a lot of bitmaps with a lot of zeros. So what we're going to do is merge all those zeros together into a single page in memory, and we'll be able to save a lot of memory. So it's extremely useful with bitmaps, and the huge benefit of that is because with the Java programming language, when you pre-allocate a byte array, all the values are set to 0. So by default, we're going to have a lot of zeros in memory. So we made another change. When we decode a bitmap from your resources or from a file, every time we see a 0 in the source PNG or the source JPEG, we are not going to write that 0 in the page. So that way the page won't get dirty and we'll be able to share a lot more memory. And the added benefit of that is we don't have to commit a lot of memory. We don't have to write out all those zeros. And that speeds up the decoding of bitmaps. So I think on some simple tests, like just decoding a bunch of icons, we're able to go 30% faster by not writing that extra memory. And we use less memory, so we go faster with less memory. So that was just to give you an idea of the kind of things that we do behind the scene on your behalf to make sure that everything works correctly. And so now we're going to look at how big objects are in Dalvik, so you have an idea of how much memory you're actually consuming every time you create a new object. So the size of an object is pretty easy to compute. You have the overhead of the object structure in the runtime itself. There's the overhead of dlmalloc. So dlmalloc is the malloc implementation by Doug Lee. That's what we use to allocate memory on Android at the native level. And then there's the data that you declare in your object, so all your fields. So the overhead of the object structure is exactly 8 bytes. dlmalloc will be 4 to 8 bytes, so most of the time it's going to be 8 bytes. And then your data, it will depend on what you're doing. So at the very minimum, and every allocation in Dalvik must be 8-byte aligned. So at the very minimum, you will have a 12-byte allocation for an object, and because it has to be aligned, you will use 16 bytes. So here are the sizes of different types in Dalvik. And as you can see, everything except a long or a double will take 4 bytes. So if you declare a Boolean as a field in a class, you're not using 1 bit, you're using 4 bytes. You're using 32 bits. Same thing for byte char. Everything is 4 bytes except long and doubles that are 8 bytes. Of course, in arrays, we're going to have a lot of those types. We don't round everything to 4 bytes, so a byte in an array will be 1 byte, and Booleans become 1 byte. So now I want to show you very simple examples. So imagine that you have an empty class. The size of that, if you create an instance of that class, the size of the object will be the overhead of dlmalloc, the overhead of the object structure. So that's 12 bytes. And with the 8-byte alignment, there will be 16 bytes in RAM. So now if we take the integer class, so java.lang.integer, it's pretty much an empty class. There's just one field, it's an int. So again, if we go through the math, we have 12 bytes of base overhead, and the int is 4 bytes. And because 16 bytes is already aligned, we're only using 16 bytes. But that means that if you have an integer class, an instance of integer, so if you're doing a lot of boxing, you're going to use 16 bytes per integer instead of 4 bytes that you would use with a simple int. So if you're not careful, that can add up to a lot of memory. And the last example is the hash map entry. So if you use a hash map, every single time you call put on the hash map, your value and your key will be wrapped by an instance of this hash map entry. And it contains 4 fields. So again, we have 12 bytes of overhead, then 4 fields that are 4 bytes each, and we have to align. That means that every entry in your hash map will add 32 bytes to the memory you're already using for your data. So if you create a hash map of integers, the overhead is going to be twice the size of the actual data. Arrays are a little bit different. You have the same type of overhead for the Dalvik object. You have the data and the overhead of dlmalloc. And there's also the width of the array to be able to do bounds checking and some padding. So the width and the padding add an extra 8 bytes to the size of an array. And must be as well 8 byte line. So a very simple example, if you create an array of 1 byte, it's not going to use 1 byte. You're going to have a total of 21 bytes, which has to be rounded up to the nearest 8-byte boundary, so that's 24 bytes. So if you just want to use 1 byte in an array, you're actually using 24 bytes of memory. So what that tells us is that all those box types, so big integer, big boolean, big float, big double, are actually very expensive. So I just talked about the big integer. A big integer is going to consume 4 times the amount of RAM that a normal int is using. So if you're using a lot of collections, and we're going to talk about them a little later, you might want to be very careful about using box types instead of primitive types. And a boolean is even worse because a boolean could be stored at the array level as 1 byte, but the big boolean will use 16 bytes.
There's also an approach, actually, let's step back. There's an approach that we use commonly internally. We're even more aware of this than most application developers need to be, necessarily, because everybody runs the framework code, right? So we need to be as optimal as possible. So where it would be more convenient and readable in our code, probably, to use booleans everywhere for flags indicating the current state of the renderer, for instance, we actually use bit fields, and we do it for this exact reason. Instead of using 32 bytes to store one flag, we use 1 bit in a bit field. So we have something like, I don't know, 70 flags in view.java, and they're stored in 3 bit fields, so 3 times 4 bytes instead of 70 booleans.
And it's the math that shows you why it can be useful. So imagine that you have a class that has 32 booleans. And I've seen classes with way more than that, like Chet just mentioned. So the 32 booleans would use up 128 bytes of RAM. So by itself, 128 bytes is not that much, but if you start creating hundreds or thousands of instances of that class, you're going to start using quite a bit of RAM. A solution, instead of using 32 different fields, you could use an array of booleans, which is going to consume only 56 bytes of memory instead of 128. So it's about half the size. But you could also use a bit field, the technique that Chet just mentioned, where every bit in your int becomes a boolean, and then you're using only 4 bytes. So that's a 32x improvement over using boolean fields. So this is why we did that in the view class, because applications instantiate hundreds or thousands of views, and if you multiply the thousands of views by extra bytes here and there, or dozens of bytes, it adds up pretty quickly.
It just starts to matter. This is kind of why we're talking about that. You may be looking at this information saying, I don't really care whether my big integer takes up 16 bytes versus 4 bytes for an int. It's more readable, it's easier to work with, I prefer the full spelling of the word, whatever it is. In a lot of cases, it really doesn't matter, and you may be wondering why we're actually talking about it. But in the large, when that scales, if you have hash maps that have to store these things in objects and they contain thousands and thousands of entries, then at that point you maybe start thinking about your data structures and the decisions that led you there and say, how could we actually compress the memory? How could we get the same functionality without taking up needless overhead in a lot of cases, simply because all of a sudden we have this bloat and we're running into the device constraints. So it's really as we scale, and in this particular case, as the framework scales and people use that view object over and over and over again, hundreds of views are sucked in. All of a sudden, the fact that we use 3 bit field integers instead of 70 booleans actually matters. So classes, inner classes also take up space, something we may not think about. You add a click listener, there's about 500 bytes of code overhead. Enums, this is a popular topic to cover.
No, sorry, let's go back.
Okay.
So the code overhead, for similar reasons you might think that it doesn't really matter, but when we have to start your application fresh, so if we killed your process and the user goes back to your application, we have to reload all your code that we may or may not be able to mmap, and every bit of overhead will make the startup time of your app be slower. So again, it's not going to matter much if you just have a single runnable. We certainly use runnables in a lot of places in the Android framework code. But if you use code generation or libraries that do that to the extreme, then you're going to start running into trouble. And again, this is really hard to go fix that kind of things in your code once your application is working, once you've deployed your application.
So enums are a topic of very popular and ongoing and infinite debate internally between people that are from the server space and traditional higher level languages and memory management, and they're all happy with the programming paradigms there. And enums were introduced in, what, Java 1.5 or something. And very powerful, very helpful, makes your code more readable. There's wonderful things about it. But we have this problem where we do need to scale the classes that we use up to, you know, hundreds or thousands of instances, and we tend to care about overhead.
So how many of you have ever wondered why we never use enums in the public APIs on Android? You'll see why.
So do many people internally, and this is why we have the debate. So you could have an enum where you have two things declared in it, and you have about a K, 1K or 1,100 bytes of size taken up. Or you could have two static ints that refer to these with 128 bytes. And this is not even doing anything with them, right? So all of a sudden you have a 10x improvement simply in the file size of DEX. So we use a lot of ints internally. Is that a question or just someone talking? Okay. Enjoy your conversation, sir. Okay, so we have the following Java programming language code here, which compiles down into Dalvik code that looks something like this.
So that's what you get. So if you just create a .java file and you put that in them, and then you compile it and you make it go through the Dalvik compiler, and then you decompile that code, this is all the bytecode that you're going to get back.
At the same time, you could declare two static ints to hold the same information, which would compile to this. That's why.
So one of the big problem with enums is there's a lot of things happening in the background done by the compiler for you. So every value in the enum is actually an instance of the enum class. So that means there's a static class initializer. Every time the first time you load that class, that enum class at runtime, we have to execute the initializer, and we have to create all the instances in the enum. So it's going to add overhead to your startup time. So we've seen that your APK is going to get bigger, but then the startup time of your application is going to be longer. And there's also a lot of stuff in the enum that you do not see in the source code. So in the source code, we just wrote, name of the value number 1, name of the value number 2. If you look at the decompiled bytecode, you're going to see that there are hidden methods that are generated for you. There are strings that are added for you in those instances. And enums are actually really useful. And we're not saying that you should never use them. By all means, use them. But be very careful. Again, if you're using a lot of external libraries, or if you're generating code, or if you're not careful and you have a large team of developers working on the same application, and you end up with dozens, hundreds, or thousands of different enums in your code base, it's going to add a lot of bloat to your application. And again, if you look at the Android API, we do use enums in some places. We just try to be very careful about where we use them and how we use them. And you should probably do the same if your application is already pretty big.
In fact, in particular, if you're writing a library that's then going to be used by other people, that's really where you have to be aware, because if that library is used and scaled to such an extent that it matters, you kind of want to be aware of that when you're creating the APIs that people will depend on. And that's the case that we're on with the framework code in Android. So garbage also is not free. It's worth pointing out that's just the way that garbage collection works in Dalvik. If you have a lot of temporary objects being created, that can hurt both in terms of the memory and what it's doing to grow the heap and fragment it. And it's also possibly harmful in terms of GCs that kick in and affect performance. So one of the things that can sort of hidden bite you if you add things like this in an inner loop, where you have a method that returns an int and then you say, I want an integer out of that. Well, then it's going to box that into a big I integer. And you, sorry, step back. Then you basically go ahead and you create an object there, and if it's just a temporary variable, when it goes out of scope, it'll be collected. Not a big deal. But if you're actually doing these things in an inner loop, so for instance, when we were writing animation code that was doing things just in terms of the data structure that it was using that was causing auto-boxing like this, then we would create these little tiny objects along the way, and then sometime during the animation a GC would kick in and it would stutter. We would lose a frame simply because we lost a few milliseconds to garbage collection. So On the whole, doesn't matter that much, but in particular cases is very important. Another one that's bit us in a similar situation was iterating. We have a lot of cases where we have listeners internally in the rendering library, and we process the listeners and do the callbacks accordingly. And if you use the very convenient for each mechanism, I love this syntax, it's so natural. So you sprinkle it everywhere, and then pretty soon you realize that you're creating iterators everywhere where there's empty lists. There's no check to see whether the list is empty before it actually creates the iterator. So it's a simple thing to say, if my list is not empty, then do the iteration. Otherwise, you're creating an object for no need at all.
And it's also APIs. So here, this is language features, but APIs can also be the cause of a lot of garbage. 2 examples, for instance, when you add something to a hash map, it's going to create a new entry object every time for you. So if the hash map is a temporary data structure collection you're using in your app, you're going to create a lot of those entries for a short period of time. String.format is another great example. It's very useful, it's very convenient, but if you look at the implementation, it's actually pretty scary. It creates a lot of temporary objects. So again, that doesn't mean you shouldn't use them, but just understand what's happening when you use external libraries or when you use even some of the core APIs, and understand the trade-offs that you are making. Because we've seen that internally. We've had apps that were running into problems. They had a lot of garbage collection pauses. And when we tried to get rid of those pauses, it was extremely difficult because all the code was relying on those APIs, was relying on the existing behaviors, and it would have been a lot of effort to fix those applications. So we had to find different solutions.
So we have some general guidelines based on some of the information we've talked about, as well as other stuff. Beware of services. These processes are always running. So if you have activities with UIs that are running in the foreground or not, well, when it's in the background, then it becomes a cache process, which we can remove from the LRU list if we need to retrieve memory. Services keep running. They don't have a UI. They're just running there in the background all the time, unless you scope the time that they run in. And that's really what we would advise, is determine the time slot that you actually need to run the service in, start it, run it, kill it. Because otherwise, we're going to start killing other stuff on the system just because we can't kill that service. So if it is possible for you to use your service for a limited amount of time, that's really the best way to go. Otherwise, you're basically creating a bad user experience for the person with the device because you have just carved out a chunk of memory that nobody else can have, and other apps will suffer because of that. It's also a problem where services can keep an activity alive. So we've seen this a lot where a service will be running and will communicate to the activity. The activity is in the background, so it would be available to be cached and to be collected if necessary. But the service, the interaction with the service is making that impossible, which means not only did you carve out a chunk for your service, but you've also carved out a chunk for your activity, which could be taking up even more because of the UI resources. Release your memory when we're running low. So there are some advisories that we send out on this on-trim memory call. This is in activity, as well as some other classes.
Service,
right.
And fragments.
And fragment. So there's different levels of the system saying, hey, something's going on, please clean up. So there's the highest one, which means, I'm done, I'm about to kill you. You should really do something about that. That gives you sort of a last chance, last-ditch effort to say, okay, I can now get rid of these resources. And then on down the way, trim memory moderate, background. These are all moderate. I think you're sort of halfway up the LRU list, which means you might be killed sometime soon. Background means you've been put onto the LRU list. UI hidden means you just became not the foreground process, which is a good time to get rid of things like I don't know, bitmaps that you can load in later or whatever. It's just different levels of system knows that it's going to have a problem. Maybe you should help it out before you make everyone suffer for it. And then the last 3 messages are when your app is actually running, but there's memory problems, which means it's going to start killing things in the background. If there are things that you can do to conserve memory, then it's going to make the user experience better because it can keep those other cache processes around.
And we do use this API on-trim memory throughout the framework. So if you go look at the source code of the platform, for instance, you'll see that the hardware rendering pipeline uses those messages to decide when to discard textures or caches of various objects to make sure that as soon as you're not the foreground application, we don't make you use too much memory and you don't get killed because we were allocating memory.
There's a significant amount of memory that's allocated for interaction with OpenGL, for example, and that is basically only allocated when it's foreground process. When we go into being a cache process. We ditched that so that the system can have that back for everyone else. Yeah,
Sure.
question?
So this method
No.
was added in Android 3.
Memory class, this can tell you how much memory your activity can have. Get memory class, the name is a bit of a misnomer. It's basically saying how much memory is there available. Get large memory class.
It's not how much memory is there available.
For your process.
What will be the maximum size for your heap? So on the Nexus 5, for instance, that method will return 192 megs, or on the G1, it will return 16 megs.
And get large memory class means that if you ask for, did we put that code in here?
No.
No. You can ask for a large heap if you're a media-intensive application, you're dealing with a lot of images, you're an image editing application. If you want to write Photoshop for Android, then you might need to use large memory class. Otherwise, you try to avoid it because basically, instead of carving out a chunk of RAM from everybody else, you're going to carve out a huge chunk of RAM. But anyway, large memory class will tell you how much heap you can have in that case.
On the Nexus 5, I don't remember, it's somewhere between 512 and a gigabyte of RAM that you're going to get with a large memory class. By all means, please do not do what I've seen people do online. If you have an out-of-memory error in your application, try to understand what's going on. Do not ask for a large memory class as the solution, because it's not a solution. You're still going to run out of memory at some point, probably because you're leaking something. And you're just going to make the device unusable for the user for no reason.
Bitmaps tend to be the area where people run into memory problems.
Yeah, that's actually my favorite thing. So
general?
bitmaps are huge objects, and I've seen many people who usually you will run out of memory when you're creating a bitmap, because they're big. And so we've had a lot of bug reports coming from external developers telling us that there's a memory leak with bitmaps. Because every time they have a memory error, it's in the bitmap creation code. It's not a leak. Like if you're asking us to create a big bitmap, we're going to try to create a big bitmap. We're just doing what you're asking us to do.
Another one that we've seen reported externally and internally is people will load a bitmap that has a very small file size because it's a compressed JPEG, and they complain that they're running out of memory because the bitmap internally is taking up too much size. The file size has nothing to do with the size of the bitmap that's created. Right? The file size is whatever JPEG wanted to compress it at, or PNG, or whatever. That's just the size that it takes up on disk. What the size that it's actually inflated into is whatever the dimensions of the image are, or whatever the dimensions of the created bitmap are. So, for instance, and all these things basically take up width times height times depth, which is 4 in general. So you've got a 100 by 100 bitmap that's going to be 1,000, 10,000, too many zeros, times 4, so 40,000 bytes. For that information, and that's a little easy to lose track of too, especially on something like Nexus 10. You have this massive screen size and you want to load in images that are going to look really good on this beautiful high resolution display, and all of a sudden you're loading in these 20 megabyte bitmaps, and you run out of memory pretty quickly, it turns out. So yeah, reuse when possible. Okay, so here's an important point. In 3.0, we made a major change to how bitmaps were managed. Because bitmaps are so tricky to deal with because they take up so much memory and people hit these out-of-memory errors a lot, they needed to actively manage their memory. As soon as they were done with a bitmap, they had to call recycle. This was not necessarily obvious to people, so they would get out-of-memory errors all the time, and it was tricky to manage them. So we decided to manage bitmaps for you. So instead of allocating the memory in native, and then having to call recycle on that memory to get the memory back, we moved that memory into Dalvik. So now it's managed on the Dalvik heap, which means when you create a bitmap, we carve out a chunk of the Dalvik heap. That's yours for as long as the bitmap stays around. When you don't reference the bitmap anymore, we can go ahead and collect it. This is much better for memory management because we can get the memory back when we need it, which is critical. It was not the way when it was allocated in native. The problem is that to get the memory back, we have to collect it. So imagine a case which is very common. I hit this with a bug with a screensaver once where on every frame they were showing a new image. It was some ocean scene, and they would show another frame in this cycling loop of bitmaps. And it was a beautiful picture, and it was the size of the screen, and it would show this one, and then the next frame it would come around and it would load the next one, and it would, it would call recycle on the old one, it would load the next one. recycle, load, on and on and on. And it was GCing on every single frame. And the problem was that it was written prior to 3.0. The app was intelligent enough to be recycling the memory, but recycle doesn't do anything as of 3.0 because it's on the Dalvik heap. We have to collect to get the memory back. So what was happening was they were creating a bitmap, and then they would dereference it and create another one. And in order to get the memory back to create the new one, we'd have to do a garbage collection. And it is a full GC. It's an expensive operation. So the fix for this, at the same time as we moved it into the Dalvik heap, we introduced an API for reusing bitmaps. So in this particular case, the fix was very easy. The developer was able to say, reuse this cache, load my new bitmap into it, so nothing ever needed to be collected. So it's basically recycling the bitmap at the same time as it's loading a new one. There was no interaction with GC required. You can read this document on it. You can check out the API and Bitmap factory for bitmap reuse. We'll also talk about it a little bit more in the performance section.
And reusing is actually a very common pattern on Android. If you look carefully, you'll see that a lot of our public APIs give you the ability to reuse data structures. So things like matrices, rectangles, even sometimes arrays of primitive types. Usually we have a variant of getters that lets you pass an existing allocated object so we can use it directly without having to create our own. So this is usually done so that you can avoid garbage collection. So ProGuard and Zipalign, those are two very useful tools. How many of you are using ProGuard already on your application? All right, it's about a third of the room. That's pretty good. If you use a lot of external libraries, you should really use ProGuard. So ProGuard can be used to obfuscate the code, which has its own merits, I guess. But what it's going to do, and it's really beneficial for your application, it's going to get rid of all the code that you don't actually use. So if you use a lot of large external libraries, you can just strip out all that dead code that you're never going to run and make your APK smaller. It would also make some of the classes that you do load smaller, so they will take less memory. Zipalign is part of the it's part of the Android SDK, and normally when you export your application from Eclipse or from now Android Studio, you can Zipalign it. So how many of you know about Zipalign? Do you use it? Even fewer people. So you should make sure that your application is Zipalign. And I think the Play Store gives you a warning when it's not. I'm not sure about that. So Zipalign basically modifies your APK to make sure that it's in a format that's compatible with M mapping. So if you run your APK through the Zipalign, we'll be able to M map all the resources, and that way we'll be able to use a lot less RAM, a lot less dirty RAM, which means we'll be able to get rid of all those pages as needed. So it will give your application even more chances to not be killed when you go in the background. Yeah, I mean, it's very simple to do. It's an awesome optimization, and you won't take any of your time. You don't have to write any code for it. So make sure you use Zipalign your application.
This is sort of a general thing that we alluded to earlier. It's that these decisions about how to optimize memory are much more easily made at the beginning as you're designing your architecture than they are at the end when the app developers come to us and say, ah! and then we have to help them try to optimize when the APIs are set and the architecture is set and there's classes everywhere and there's suboptimal practices everywhere because they weren't thinking about it ahead of time. It's much easier to write it the correct way to begin with than to redesign it later when everything's set and all your developers have left the team and nobody knows how the code works anymore. There's a lot of intricacies about how the language works that are important to know. We talked about some of those earlier, the sizes of objects, the details of auto-boxing. Just know about the language so that you can use it effectively and make the correct trade-offs between enums versus ints, integers versus ints, whatever, objects versus bit fields. Again, just sort of know what you're dealing with and know what the trade-offs are when you write the code for the first time. Abstractions in general have a lot of hidden costs. It's nice to have models of abstractions and layers of indirection. It's all very pretty, but it may make it harder to understand where the problems are. It may make it harder to tune. So understand why you actually have these levels of abstraction and abstract in an optimal way for this constrained platform.
So here's a practical example. We've done a lot of performance tuning in the Play Store application, and one of the issue was garbage collection. And the problem was the Play Store application was not reusing bitmaps like we just talked about. So the obvious solution to reduce garbage collection and to make scrolling smoother was to just reuse bitmaps. The problem was the code that was responsible for loading bitmaps was under so many layers of abstractions hidden away in the app that it was way too much work for the Play Store guys to be able to use that solution. And I think they still haven't done it. They want to do it, but it will require pretty big refactorings and a lot of work on their part. And they have other priorities. So this is another great example of, you shouldn't optimize too early, but definitely keep optimizations in mind, especially for some of those big points that we talked about, like bitmaps. Make sure that you have a way to optimize those things without having to refactor or re-architecture your entire application, because it's going to be very, very painful to do it later on.
So reusing other people's libraries or even your own is a great idea because someone's already solved this problem. Why should you solve it? It's not necessarily a great idea in every case for the Android platform because those libraries were not necessarily written for Android or for mobile or for the constrained device situations that we're talking about. They've got layers of abstraction in their library. They have ways of doing things either in their API or in their implementation that you may not be aware of. You have a hard time getting the details out. If you're using this library, it's this opaque black box, and you see that it's generating a bunch of garbage, but you're not actually sure why or what you can do about it. It's a little bit easier. Maybe it's a pain to write it on your own, but you should at least be aware of what the library is doing and make the correct trade-off between the ease of development of simply using that library versus the complexity of debugging and optimizing something where you didn't actually design the thing for your target platform.
There are also sometimes hidden costs. You might use two libraries in your application, and both libraries do their own logging for errors, and they use different logging frameworks, so you're pulling in even more code than you need to in your application, so you're going to have to load more data and stuff like that at runtime. And when you choose a library, the primary question that everybody asks is like, what does it do for me? And that's a great way, it's like, it makes my life easier, you should definitely use that library. But try to think how it does that, how does it do that for you? A great example, for instance, we've seen applications, even internally, they were using those fancy libraries that do a lot of introspection using annotations and dependency injection, and that's great, it makes the code cleaner, it helps working with large code bases. But then one of the drawbacks was the startup time of the app was getting really bad because so much code was running, and it's pretty inefficient code, for instance, to check annotations or to do reflection. And there's nothing you can do about it. Like if your entire app is relying on that behavior, then you're stuck with that library or similar library. So be sure to understand the trade-offs when you choose a library. And again, it doesn't mean you don't have to use them. You can use those libraries, but you don't have to use them in your entire app. You can have parts of your app where performance matters, and in those parts of the app, you can be more careful about what you use. So try to think about what's happening behind the scenes when you use foreign code.
And this can still be the case if these libraries were written for Android. So maybe they were written, more optimally for the mobile device space, but still they have the problems that Romain was talking about, where maybe they duplicate things that are going on in your code, so you have code bloat, or in fact it's still a black box, so that when you go around to optimize or understand your architecture, you really don't know what's going on there. So make sure you're actually using it for the correct.
It could also be that the library was never tested for something at the scale of your own project. I mean, I've done that myself. Like, you write a small utility library that works really well in your simple applications, and then somebody with a much larger application uses the library, and suddenly the overhead of your library becomes obvious because it runs so much more, and then the entire application is affected.
There's also an assumption that ProGuard, which we mentioned before, can help with the situation because it's going to magically strip out all the methods that are not actually used by your application in that library. But the dependencies tend to be tricky. There may be things dragged in which you don't use directly, but are dragged in because this other thing referred to it, and all of a sudden you've got 90% of the library stuck there anyway, when really all you wanted was that 5% of it that you brought it in for. So just be aware.
So to help you optimize your applications for memory, we offer a set of optimized containers. So we have two types of containers. The first one is called sparse arrays, and they basically can replace hash maps when the key has to be a primitive type. So instead of using a hash map of capital I integers, you can use sparse arrays. And we have different variants of a hash map depending on the type of the key and the type of the value that you want to use. The two big benefits of sparse arrays is that they're allocation free. So when you put something in a sparse array, we're not going to create an instance of an entry wrapper around your key and value. We might have to resize the underlying storage array, but other than that, there's no allocation. And there's no boxing. Like internally, if you look at the source code of the sparse arrays, it's pretty simple. We just declare an array of ints and an array of booleans or an array of doubles, whatever you pick. So they're very efficient for that. So these are all the variants of sparse array that we provide. And they're equivalent for hash maps. So if you do integer to object, it's sparse array. Integer to boolean, we have the sparse boolean array. Integer to integer, sparse int array. Integer to long, long to object, and long, long. The long, long one, the long, sparse, long array, the name is a little weird.
It's a little long.
Is not, for some reason, we forgot to make it a public API. So if you need one, just go copy it from the Android source code. It's a purely standalone class. You just have to extract the file, change the package name, and you're done. And some of those, don't remember which one, but one of them, I think the long sparse array was added later on, and it's available in the support library. Support library, so the long sparse array is in the support library, or the sparse long array, one of the two, and the other ones have been part of the framework for a long, long time. And again, if you need them, they're very small, they're all standalone classes, so you can just copy them in your application. And then you can adapt them to your needs. And we definitely use them extensively throughout the entire framework because I was talking about external libraries and the hidden cost of using external libraries. And we try very hard on Android to not have hidden costs on your behalf. So we try to use sparse arrays all over the place so that we do not create garbage when you invoke some of our APIs. So here's an example of the benefits of sparse arrays. So let's imagine we have a hash map of integers to integers, and it contains 1,000 elements. So that's not that many elements, and integers are pretty small objects. And this is the content of a sparse int array. So if we compute the size of an instance of a sparse int array using the math that we've seen before, a sparse int array of 1,000 pairs of integers will take up about 8 kilobytes of RAM. So that's pretty small. Now, the same map using hash map, so that's what an hash map contains. There's a lot more stuff. And it's going to use about 64 kilobytes. So it's 8 times bigger than the sparse array. So again, if you're using, if you have a hash map of just 3 or 4 elements, it's not a big deal to use a hash map. You should still use a sparse array if you can. But as you're using more and more elements, the overhead of the standard hash map will become pretty significant. How about tree set? Sorry? Entry set? Which one do you mean? The one right here? Yes. What about it? You mean on sparse array? Yeah. Oh, yeah, probably. I would have to look at the source code to see how it works. It was there for convenience. I've never used it myself. Probably not. Yes, but so again, to iterate over a sparse array, the way you would do it is to not use an iterator. It's usually a bad idea.
So the intention with the sparse array classes as well as array map, which we'll talk about very soon now, was to match the API, so it's an easy swap in for what you maybe used to be using, like hash map. So you can just go ahead and use this thing instead. So it needed to expose the same API. That doesn't mean that all of the methods in that API are ones that you should use to get optimal performance.
And since we provide the source code, you can go take a look at it and see what it does.
And you can also take a look at the documentation, because it's pretty clear about which methods are suboptimal.
Sorry? We could do, yes, we could use a single array of ints and interleave the elements. But make the code a little more complicated, and the benefits, at least for what we're doing, we didn't need the benefits. If we ever need to do that, we will. But we will not add complexity that we don't need. You can definitely do that if you want. Another optimized container we introduced in Android 4.4, and that's in the support library, is called the array map. It can replace hash map. So the benefits are similar to sparse arrays. It doesn't, so it can replace HashMap for any type you want. It uses generics. So it's not going to do allocations, so it's not going to use entry wrappers. It's still going to have to resize an array as needed. The API is compatible with HashMap, so it's almost a drop-in replacement in your code. You just have to search and replace HashMap for ArrayMap. And we have a version of it, like I said, in the support library. One of the only issue with ArrayMap is that it's going to be a little slower than HashMap. So if you do a lot of access or if you have a lot of elements, you should prefer a HashMap. For anything in the few hundreds of elements or maybe low thousands of elements, ArrayMap will work just fine. But if you're in your application, you have dozens of thousands of elements, you should make sure that ArrayMap is as fast as you need it to be. And finally, when you can use just normal arrays. And this is what, for instance, I've done in Android view group to store all the children of the view group. View group is a class that's, whose code is executed all the time. And it wasn't as much about saving memory, but to save execution time, because we can access an array directly, so we don't have to invoke extra methods or go through interfaces like a list. And it was actually measurable, given the number of accesses we were making per second. It was a benefit.
So there are different tools that we provide to measure what your memory use is, so you can have ways to actually optimize your application. First of all, let's talk about the kinds of memory that these tools will give you information about. There's essentially two kinds of memory you care about. There's the unique set size. This is the stuff that your activity is taking up directly. This is the private clean plus the private dirty in the tables, the information we're about to see. And it's the RAM that only that process is using. This means that when that process is killed, if it's a cache process and gets removed from the LRU list and destroyed, that memory will be directly returned to the system. In addition to that, it's proportional set size, which is essentially that same memory plus the shared memory that's occupying. But that's proportional to all the different processors that are using that same shared memory.
So for instance, we mentioned the Zygote earlier. So let's if the Zygote takes 10 megs of RAM and we have 10 applications running, for the PSS, we're going to add the size of Zygote divided by the number of processes. So in that case, we would add 10 megs divided by 10 processes. We would add 1 meg to the USS to compute the USS, to compute the PSS, sorry.
So meminfo is a tool that's been there for a long time. You would run this, you would get this information by running ADB shell dumpsys meminfo. You can also run it directly from Android Studio.
Yeah, we'll show you a screenshot on how to run that tool from the IDE.
And you get out a lot of numbers. This looks kind of like a blue screen of death. A lot of information here, not exactly clear what's going on. So we want to walk through some of the stuff that you would actually care about on this screen. There's the native heap and the Dalvik heap. This is the memory that's been allocated by your application, the native and Dalvik levels, directly or indirectly. And then the heap allocation. So let me see if we walk through here. So we've got, so you'll notice that the PSS total is larger than the private dirty. It's also larger than the USS. Wait, USS is PSS total. See? Private dirty plus private clean is USS. But the PSS on the left is larger than that because it contains the proportional size of the shared memory that it's also occupying. We're moving on. We see some native allocations, the .so. This is the memory taken up by native libraries. Interesting part here is that most of this is dirty. You would expect if we're just mapping in native libraries that they would come in as clean because they're just library code. However, we need to actually move those pages around as we map them in, so that becomes dirty pages.
So in the APK mmap, you can see the private dirty is at 0 and the private clean is at 500. So the APK mmap will be for your code or for your resources. And in that case, it means that because private dirty is at 0, it means we are able to mmap everything as clean pages. So if the system needs memory, we'll be able to reclaim 500K of memory knowing that that data is on disk. So we won't have to kill the application. So your application is effectively half a meg smaller than it seems to be.
Dex mmap, this is the code that was mapped in for your application, mostly clean, so that's all good. We can mmap that in and out. Graphics and GL, this is new information that we provide in meminfo in Android 4.4. this was memory that your process was always taking up. We just couldn't report it before because we didn't get the information back from the driver. But now the drivers are reporting more information to us, and we're reporting it to you. This is memory that's taken up by graphics GL context, data structures at that level, texture memory, I don't know, the buffers for the screen, I think, are part of that. So looks like a lot of memory. It always was. It's just that now we're actually telling you about it. And then finally, the total memory on PSS and USS. And that's pretty much it. There's other information that's part of that same output. You can see information like how many windows your activity is currently using, and how many activities there are. This is a good one to keep an eye on because it tends to be easy to leak activities. I know because I've done it a few times. If you run your application over a long period of time, let's say you rotate the screen back and forth, and then you run meminfo, and you see that all of a sudden you have 7 activities, and there's only one window on the screen. What's going on? It's probably because there's data structures that are retaining references to activities, and those get retained between the configuration changes, and each activity can be a huge amount of resources, so you want to make sure that you're not leaking activities in general.
It's not highlighted here, but you can see also the number of views that you've created in your process. So try to keep that number as low as possible.
That would be nice.
It makes me very sad when I see large numbers here. When you invoke meminfo, so we've changed meminfo a little bit, sorry. And in Android 4.4, to get the dump of meminfo, that's very similar to what you would get in previous versions. You have to use the flag -a, and the 2 extra columns we're showing are about shared memory. So if you look at it, if you look at the Dalvik heap in shared dirty, we have 7.5 megs of memory that we've pre-allocated on your behalf and that we can share between all the processes. So that gives you an idea of the size of the framework and APIs on Android and how much memory we save by sharing it between all the applications. Dalvik other is just extra stuff that Dalvik uses. For instance, it's the JIT cache or garbage collection information. And if you look at the shared clean and you look at all the M-maps, you can see that we're able to M-map a lot of stuff, again, on your behalf, and we can share all that between our applications. So we have 17 megabytes of shared clean memory that are shared between all the applications. So it's a lot of code, so .sos, a lot of DEX, that's all the framework code, and about and a couple megs of fonts and assets. So now before we talk a little more about Dalvik, I want to go through a little exercise. So this is a dump application I wrote this morning. So I created a class called chunk. It contains a byte array that's a megabyte of bytes. So there's a little bit of overhead like we've seen for the class in the byte array, but let's not worry about that. And then I wrote this little loop. So we have 2 lists. We have the retained chunks and the temporary chunks. Then we look at the maximum memory coming from the runtime class. So max memory will tell you what is the maximum size that your heap can be. So on the Nexus 5, like I said before, it will be 192 megs. So we're setting our max at the max memory of the heap minus 1 meg. And then we use total memory to know how big the heap currently is. So what we do is we allocate a new chunk, so basically 1 meg of RAM at a time. And we do that until the heap is completely full, until we're almost to the point of getting an out-of-memory error. And every other time, we put the chunk in one of the lists, and the other time we put it in the second list. So we have 2 lists. They contain about the same number of chunks, so chunks of 1 megabyte of RAM, and our heap is completely full. We've allocated about 190 megs of RAM. So this is the code that verifies what we've done. We log the max size of the heap. We log the amount of free memory and the total size of the heap. So after running this loop, this is the result we get. Our maximum is 192 megs of RAM. We have less than a meg of memory free in the heap. And the total size of the heap is currently, there's probably a rounding error because of floats. We have 192 megs of heap currently allocated. So we have less than a meg of free memory. So now what we're going to do is clear one of the lists of chunks. So we're going to get rid of half of the memory we've allocated. And we force a GC. You should pretty much never call system.gc in your application. I can do it here because, well, I'll do whatever I want. I have the mic. And if we run our logging code again, we can see that the GC did its job. And we have about 88 megs of RAM available in our heap. And the heap still has the same size. Now, what's going to happen when we try to create a bitmap? So how many of you think that allocating this 2 megabyte bitmap will work? I know, I'm asking people to raise their hands. At least one guy said that, okay, well, one guy is wrong. So it's gonna fail. We're gonna get an out of memory, and the messages in the logs are very confusing because it's telling us that 46% of the heap is free. We have 106 megs of RAM available, and we failed allocating 2 megabytes. And that is because Dalvik does not compact the heap. So you can fragment your heap very easily. And that's also why garbage, like temporary garbage, we talked about temporary garbage and all the GC pauses, but it can also be a big issue because it will fragment your heap. And I've actually seen applications, real applications on the Play Store where developers were confused because they were running out of memory, and when they inspect the logs, they see they have plenty of memory available. The bad news for you is there is no good solution to this problem. The only thing you can do is if you know you're going to need a big allocation somewhere in your application, if you write a photo editor, it's pretty obvious you're going to need a big bitmap. You can pre-allocate a giant byte array and try to be very smart about calling system.gc to make sure that you're always holding onto those bytes in a single contiguous space at any given time. But if it ever happens in your application, especially on older devices, because on newer devices the heaps are so big that it's unlikely you're going to run into this issue. But if you ever see that in your logs, you know why it's happening. So Dalvik doesn't compact but can shrink the heap if there's unused space at the end. Doesn't happen that often. And can also use the madvise API for the kernel. So if you have, even if your heap is fragmented, if it has pages of empty memory somewhere in the middle of the heap, Dalvik can give those pages back to the kernel. So it will look like your heap is taking, let's say, 192 megs of RAM, but actually it will use less physical RAM than that. But you could get in big trouble if you try to use those missing chunks later on. And hopefully this will get better and we'll have a compacting GC at some point in the future.
That would be nice.
Yeah, why don't you get on that?
So there's a couple of tools that are useful for tracking memory leaks as well as memory allocations that we'll talk about here. One of the issues with using what we're about to talk about now, which is the MAT tool or JHAT, hat analysis, heap analysis tools in general, is that the Zygote allocations are not something that you should care about because these are the shared pages. They're clean. We map them out. You really shouldn't be tracking information there, and it tends to confuse the tools. So you need to run a command line tool called hprofconf first, and that will convert your hprof dump file into something that actually makes sense to the tools. So we'll step through using the hat tools here. So first, this is a snapshot taken from Eclipse. There's something similar in Android Studio. You would first take a hprof dump. So this will dump all the information about all the current allocations out to a file. So you select your app, you dump this file out, you save the file, and then you run the hprofconf tool on the resulting file. And that gives you your converted hprof dump. And then there's two ways that you can look at that information. One is using JHAT. So here I ran JHAT. This spun up a process, and then in my browser I went to localhost :7000, and then that loaded in the top level information for the dump. There's a whole lot of information there about all the objects that exist, and then there's different links you can follow to get a histogram of that data, to trace the references to the root set. It's kind of a mystical art actually using these tools, and you tend to have to spend a while with it to sort of get into the mode. But it is basically the most effective way that you can trace leaks in your application.
So especially JHAT, I spend way too much time in my life looking at the output of hat and JHAT. And with a lot of practice, you will be able to figure out what's going on. But if you use it for the first time and you have no idea what you're doing and where to look at, don't worry, that's normal. Just keep staring at it for a few hours, and then
Exactly.
it will start making sense.
I think that the big idea is that you want to trace references. You want to see everything that is referred to from the root set, which means all the way up, which means it can't be collected. So excluding weak references, links to the root set, and that's going to give you the tree of objects, and you will eventually magically see the leak in there somewhere. Recently I was chasing an activity leak which I caused, and I was able to see that information by using a combination of JHAT as well as a MAT. which is the memory analysis tool. It's a plugin for Eclipse, so you can get a standalone version as well that's based on Eclipse. And it gives you very similar information, also gives you a little bit more analysis. It has different ways of slicing and dicing the data. There's a very good tutorial on chasing leaks in general that uses Matt as an example by Patrick Dubroy, who used to be on the Android team. And I put a link to the YouTube video here. But you can find it in one of the Google I/O YouTube playlists. So I would recommend watching that if you ever get into using Matt. So there's a general process that we use for finding leaks. You basically run the app for a while, and then you get a dump, and then you spend a long time looking at the output to try to figure it out. You can also take a look at meminfo, the stuff we were talking about before, to find out where some of the large problems are. Are we allocating a lot of stuff on the native level, or the Dalvik level, or are we leaking activities? Is there anything that really stands out as a huge number which you don't think is proportional to what your activity should be experiencing? The easy thing is finding the large leaks, things like activities or really large bitmaps. Those are kind of fun to chase because basically you just see this huge number stick out in the references somewhere and you go, that's the guy, and then you can click through and find out who referenced him. But finding the lots of little objects is a bit harder. You might spend some quality time there.
Yeah, Matt actually has a very interesting feature that Jet Haase doesn't have. You can tell it to do a diff between different dumps. So you can run the app for a while, take a dump, run the app again, and then you can do a diff between several of those dumps and look at what objects have been allocated in the meantime. It's a great way to find the leaks.
That's also the basis of the other tool we wanted to talk about, which is Allocation Tracker. We've talked about this tool a bunch already. This has been in the tools for a while.
Question. Have you guys used that tool before? Raise your hand.
Oh, totally useful, especially for inner loop tracking or allocations during animations is where I used it quite a bit because I wanted to find out why we were experiencing GCs when any animation was run, and I used Allocation Tracker
Actually,
for that.
Speaking of animations, you guys should, if you want to try to use Allocation Tracker, see what it does, go run it when an animation is going on using Chet's APIs, and you'll see that Chet allocates a lot of stuff when you run an animation, especially a lot of hash maps.
But what the animation classes don't do is allocate during the inner loop. So as the animations are actually running, they're not doing any object allocations for each of the frames. They do allocations to begin with, especially things like layout transition or the new transitions APIs. They allocate things like array map and sparse arrays because they track information for before, after states. But during the actual animations, nothing should be allocated. At least it's not at the framework level. It may be in your application, and the way to find that out is to run an animation, and while the animation is, after it's started, click on the Start Tracking button, and then at the end of the animation, or maybe toward the end of the animation before it's done, click on the Get Allocations, and see all of the objects that were allocated while the animation was being played. And that will give you an indication of whether there's stuff that you're doing to generate temporary GC along the way that maybe you could avoid.
And an animation can be, scrolling a list, and if you run the Allocation Tracker on random applications, you might be surprised by how much data is allocated by applications out there. And very often, it ends up being, random libraries like a JSON parser that's not very optimized. And again, that's why you should understand what the libraries are doing. So use Allocation Tracker. It's a great way to figure out what's going on.
So the way we use it in general is start tracking and then get allocation. That basically tells you all the objects that were allocated between those 2 points in time. Then you click on one of the items that you care about, like a bitmap that got allocated or an integer that got boxed. And then down below, it will give you the stack trace where that allocation came from. And I think it'll even, in Eclipse, will pop up the code associated with that. So you can really track pretty quickly from the allocation that you care about that you don't think should be happening to the code that actually caused it to be allocated. Great tool for Jank. Processes. So every time you start a process, there's some amount of overhead, maybe 1.5 meg just for that process. There's a bunch more when it's actually about to show its UI, and when it's actually showing its UI and taking up things like window buffers and GL textures and all the rest of the stuff that it takes up, it's allocating even more. There is a technique that some applications use to have multiple processes. In some cases, maybe it's necessary because maybe one process is going to be long-lived, media server or something, and another one is going to be a process for showing the UI associated with that media. This is the way the music app works, for example. But in general, try to avoid multiple processes because each of those things takes up more overhead. There is a way that you can force multiple activities. I mean, obviously you can have multiple activities in the same application, but even if they're more separate activities, you can force them to use the same process by using the Android process attribute in your activity tag. There's a new tool that was introduced in Android 4.4 called Procstats. We introduced this. We'll talk about this more in the What's New talk tomorrow. But there was a lot of effort spent on optimizing the memory that we're taking up simply in the platform so that we can target these lower-end devices and actually work reasonably well on a 512 megabyte device. And one of the tools that we used for doing that was the new Procstats tool. So you can see the output here. There's a UI that you can use, or there's a command tool if you want to get really geeky and get a little bit more information. You see the initial screen on the left. So there's an indicator of how much time in the sample time that it's spent in a critical situation or a moderate situation or a normal situation. And these relate to those trim memory calls that we saw earlier, whether it was actually in the process of having to kill some apps to get that memory. And then it shows you the top processes that were taking up memory. The percentage that you see is the amount of time that that process was actually running during this period. And in general, you don't want that to be 100%. If your activity was backgrounded for all of that time, and yet it's taking up 100%, what is it that's causing your activity to be active? Are you also running a service that was talking to it at the time? And then the blue bar, you would think it would be related to the percentage, but it's not. That's actually the relative weight of that process. So that indicates how much memory it was actually taking up. So there's the amount of time that it was spending running, and then there's the actual amount of memory that it was taking up while it was running to give you an indication of how bad the situation is for each of those. And then you click on one of those, and you get the screen on the right, and it gives you more information about how much memory it's taking up and some of the reasons why that activity was awake at that time. Maybe a service was talking to it.
So that's just the command line version. We won't go into details.
And
so,
this is the last slide.
If you want more information, there's an article that summarizes everything we talked about here today on developer.android.com. If you go to the training section, there's an article called Android and RAM, I think, just like this talk, or Memory and You, something like that. And we're going to take a break for about 15 minutes. And in the second part, we're going to talk about performance tips for applications. It's going to be about graphics, layouts, views, and a little bit more tools that you can use to improve your applications. So let's come back at 3. It's
3 o'clock.
2:48. Yeah.
See you then.
Thank you.